So last week, okay, are we there? Now, so like I said, all the models considered so far have been deterministic in nature. And we have aimed to describe what is likely to happen on average in the population. So our aim for the past 1 week has been, on average, we are looking at the mean. Deterministic look at the mean or the average of what is going on in a particular population. So leaving out the aspect of the variance. So, but in this lecture, we'll be looking at both mean and variance. So we are in this section going to introduce the method for setting up stochastic models which incorporate chance variation. By the end of this course, fellows should know how to set up stochastic models, understand the difference between three key approaches for setting up stochastic models, know how stochastic models are used to generate prediction, know some of the areas of application of stochastic models, and the insights that stochastic models can provide. So all the model considered thus far have been deterministic, like I said. So this means that they are essentially fixed clockwork system. Like you already know what you get. You understand? It's fixed. So when you have an initial condition, you know what's going to produce for you. But for stochastic, there are a lot of random, so you cannot really predict. A lot of uncertainty that comes out because of so they look to be unpredictable. So given the same starting condition, exactly the same trajectory is always observed, deterministic. So if you have an initial condition, exactly the same trajectory is always observed. So such a Newtonian view of the world does not apply to the dynamics of the packages. You understand? So you find out that, if you take, for instance, if you are going to predict for so you want to predict for infectious population or the number of cases over a time. So so you find out that you are likely not to get less than what you started with. So if you have cases, number of cases of malaria or any disease, then it's behaving this way over time. And then maybe this is up to 2025. And we want to see what is going on. For a deterministic there, you want to see what will go on after maybe from 2025 to 2020 and 2030. So for deterministic model, you are likely to get the same kind of trajectory, which is not really true. So, and then it's difficult for you to predict with that. So, but for stochastic model, it gives you different kinds of observation. It gives you more than one, and then you are between so many intervals of your prediction. So, and then you can have just like the one I showed last week. So, if it were possible to rerun a real world epidemic, you will not expect to observe exactly the same people becoming infected at exactly the same time. So it may not mean that at certain time in 2025, we are in June, right? June 2025, 2025, June 23rd, and then June 23rd, 2026. The deterministic is saying that today we had 100 people infected with malaria, and then in 2026, still 100 people. You understand? So it's not really realistic. So clearly there is an important element of chance. So stochastic models are concerned with approximating or mimicking this random or probabilistic element. In general, the role played by chance will be most important whenever the number of infectious individuals is relatively small. So, like we said, at the beginning of an epidemic, the randomness of the random nature of the epidemic is highly observed because there are very little number of people that have been infected. So the way the disease is getting transmitted from one person to the other, follow a very strong random nature, and with that you can really capture um, stochasticity, especially at the beginning when the population size is still very small. So when an infectious disease has just invaded, when control measures are successfully applied, or during the trough phase of an epidemic, that means when the epidemic is going down in the trough, the peak is when it's high. So in such circumstances, it is especially important that you are taken into account and incorporated into your model. So this section details three distinct methods of approximating the chance element in disease transmission and recovery. One, introducing chance directly into the population variables. The population variables are S, I, R, basically. I mean the number of susceptible, number of infectious population, number of recovered. These are the variables. And then two, by random parameter variation. Now, in your basic SIR, you find out that the major parameters are the beta, the recovery rate, the alpha, and then in case where you factor the gamma, where you factor the which is the natural death, you have. So some of you can subject each of those, like for beta now. I mean, the rate at which people are infected is a function of probability that the person will be infected given an infectious contact. The beta is equal to PC. P is the probability of infection given an infectious contact. You understand? So this is between 0 and 1 because, it's possible that somebody get a contact and then C is equal to the contact rate. So this one is, it's a probabilistic situation because find out that is it every infectious contact that leads to transmission? You understand? So you have to, so it's probabilistic. So if it leads to transmission, that's 100%. You find out that the person will be infected for it to be 0 and 1. So now, so that's why we say that the beta there, which is the transmission rate, can be subjected to some kind of stochasticity. Understand? The function can be, you can put stochastic variable into this beta, and then you subject it to stochastic. So the beta, because you find out that it's influenced by some noise. Now, another aspect is individual level explicit modeling of the random events. Now, we said the other time that there are factors that influence your transmission. One of it is your nutrition status or your genetic factor. So there are certain people that we said they can never have HIV. They can't because of their genetic factor. Now, there is also a role your nutrition status play in disease transmission. So all these things have an influence. So there is always a kind of chance, and that is why when you talk about immunity is a very elusive phenomenon because the immunity of Mr. A is different from the immunity of Mr. B. So immunity is a function of your genetic factor, your nutritional status, and a lot of other things, underlying mechanism in the system. So that's why, when it comes to some very strong epidemic disease, like for COVID, find out that everybody were asked to be vaccinated because you cannot depend on the natural immunity. You understand? Because immunity varies from different person to another. So all these examples have two elements in common. First, they predict different outcomes from the same initial condition. So you find out that you are given the same initial condition, maybe I of 0, x of 0 is equal to the same thing. But at the end of the day, they are giving different outcomes. And that's where chance is coming in. And as such, multiple simulations are required to determine the expected range of behavior. So, second, they all require the use of random number generating routine. This can be thought of as rather clever computational trick that can deliver an apparently random sequence of numbers in some prescribed range. Now, to enable a fair comparison of the different methods of implementing stochasticity, we primarily focus on the SIR model, and then we build some complexity to SEIR, and then we see. So, model with bets and debts, with which in a deterministic framework was always convert to an equilibrium in an oscillatory pattern. The oscillatory pattern, the oscillatory dynamic show that okay, there's a wave, and after some time there's a damp in the oscillation. Now a wave starts, and then after some time it's going down. The reason is because the disease is going to extinction. Once the disease is going to extinction, the wave starts reducing, and then there's a damping in the oscillation. Now, we also utilize a constant set of parameters, R naught, which is equal to 10, and over gamma is equal to 10 days, with the average, that's the infectious period, and then the mu, that's the natural deaths, which correspond to the mean, the average life expectancy of 50 years, and the constant population size. For stochastic models, you need to consider both the long-term behavior and the short-term transient dynamics, as well as study both the mean and variance of the number of infected cases. So for the deterministic, we have been only looking at the mean number of infected cases. So that's why when you are plotting, take for instance, I'm plotting when you have SIR, and I'm plotting using you have your SIR, so the I, which is the number of infections. So over time, maybe your time is in days, then you start from 0 to 1 up to 10 days, and then the thing is going like this. It's just so you only take an average of the number of infections. This is not giving us a kind of a range where you have the variations. Now for stochasticity, you are having, multiple, you can run the simulation as many times as possible where you are having different kinds of, for the same infection, you have different kinds of, and at the end of the day, what are you doing? You are trying to see, okay, not just one single outcome for many simulations. So it's giving you that the number of people infected between, let's say, this is 500. So between 0 to 1 day, or let's say between 0 to 2 days. If you take, for instance, from here, maybe this should be 100, and then to this last one, maybe this should be 1. So it's going to be from 100 to 1000. But if it is just the deterministic, it's only one. You understand? So which is not always a realistic situation. So now the deterministic just take the average, and then you are not getting the full picture. So because stochastic models have close relationship to integer valued or individual based models, we generally deal with the number as opposed to the proportion of susceptible and recovered and label at X, Y, and Z. Now, 5 key features distinguish stochastic model from their deterministic counterpart. Although not evident for all forms of stochastic models, these features can have profound impact on epidemiological dynamics and will be a consistent theme throughout this section. In brief, these distinguishing features are: 1, variability between simulations. Variability between simulations. So now I want you to be careful of some of the background I'm building because they are very important to what we're doing from now on. So if you don't have the theory ethical background, as you do all the simulations, you may not be clear with some of these things as you go on. Now, the most obvious element of any stochastic model is that different simulations give rise to different outcomes. You can see that if you see simulation 1, the outcome is different from the last one. The first one starting from 100, the other one, the last one is 1000. So the range is between 1000 and 100. So we are saying that different simulations give rise to different outcomes for a stochastic model. This implies that although the general statistical properties such as the mean and the variance may be accurately predicted, so it is generally impossible to predetermine the precise disease prevalence at any given point in the future. You cannot be here now and you say that, oh, we are going to have 1000 cases, like for the deterministic, you can predetermine. It's predetermined. You understand? Even the initial condition is predetermined. But for stochastic, no, it gives you the range. So you cannot say we are going to have a fix, but more or less you are going to have a range, not a fixed value for any outcome you are coming up with. 2, you have variances and covariances. Variances, these are the features of a stochastic dynamic model. So the continual perturbations caused by the random nature of stochastic equation leads to variation in the prevalence of disease and the number of susceptible. Additionally, the interaction between stochasticity and deterministic dynamics generally causes negative covariance between the number of infectious and the susceptible individual, which in turn can cause the mean population levels XY to deviate from the deterministic epidemic. So there are variances between the susceptible, the infectious number in the population, and this is obvious even from what we saw here. So we also have the case of increased transient. Stochastic perturbation away from the epidemic solution are countered by the generally convergent behavior of the underlying deterministic dynamics when far from the endemic equilibrium point. These restorative forces are usually strong and dominate, so that the model acts much like the deterministic, just increased transient. You are just seeing something that is moving and then appearing, and then after some time you don't see anything afterwards. So the equation of stochastic model can be conceptualized as resulting from random perturbations away from and transient-like return toward the deterministic factor. Why? As the population becomes very large, due to the law of large numbers, so stochastic behavior will be paralyzed. So it ends up to become a deterministic. So now all the behavior you are seeing initially will just vaporize. Now stochastic resonance, as most SIR type disease models approach equilibrium in a series of decaying epidemics. Like I said, the oxidation is damping. Now the increased transient-like dynamics of stochastic model leads to oxidation close to the natural frequency. Now, thus, stochasticity can excite, and around the normal endemic prevalence, leading to sustained cycles. Like you are having a continuum that you cannot predetermine, just like what I was showing there. Then you also have these stochastic extinctions. Now, those probability models that are integer value may additionally suffer from stochastically driven extinction. So in closed populations, chance mutation will always result in eventual disease extinction. Now, irrespective of population size, long-term persistence requires the import of pathogens from an external source. Similar extinctions may occur during the early stage of invasion. Now, we were saying that just like we have the final sites in the epidemic, when there is an epidemic, you have this kind of stuff where the disease is increasing, and then maintain this kind of stable roots, and then at the certain time it started going down, going into extinction. Now, the stochasticity also have this kind of property where you have the disease is increasing exponentially, and then at a certain time it gets to the top. That's, we call it the peak of epidemic. So at the peak of the epidemic, the likely thing that can happen is that some people are already getting maybe either natural immunity or using certain interventions. So for you to see this kind of drop, it's either people have a natural immunity or there is a drop due to treatment or vaccination. So at this point in time, the disease is entering into extinction, and then you are having a downward trend, in what is going on. So now, epidemiological data are very noisy. They are noisy. So two types of noise. We have the observational noise or error. Data are probabilistically related to the true state of the system. Now we also have the process noise. The system progresses probabilistically. So under that we have the environmental noise. So where you have some parameter, the random variable, and then demographic noise, individual level chance events. That means demographic noise in terms of age, in terms of gender, in terms of occupation, socioeconomic status, and all of that. There are a lot of variability. Everybody does not have the same educational qualification. You don't have the same age, so there are variabilities in that variations. Even as we are seated now, we have an heterogeneous population in terms of qualification, in terms of age, in terms of gender, and all of that. So these are demographic things. They affect the result of the epidemiological data in some ways. Now, observational noise. The simplest form of noise that can be introduced into disease modeling is observational noise. For this approach, the underlying epidemic dynamics remain the standard deterministic differential equation, but there is assumed to be some uncertainty in the recorded data. We're talking about data now. When you talk about data, especially observational data, there are two things: reported and unreported cases. You understand? The best data so far in epidemiology that has been used, reported data, is 60% quality. And that's UK peak amount, 60% quality. So when you talk about some of these data, they're influenced by the observational error. Now it's either the person that is recording did not record the right thing, or due to diagnostics. Now you test somebody that like one of my PhD students took his daughter to the hospital. He was feeling very hot and all of that, and then on getting to the hospital, she was diagnosed, and then diagnosed, he said that he was negative to malaria. You understand? Negative by RDT. RDT is the normal thing they use to test you. So it was negative, but because the girl was showing symptoms, so they have to force her to be positive. Yeah. So they recorded her to be positive. So that's where the error comes from. So in recording, you are recording somebody who is negative will be positive. So maybe the symptoms you're showing may relate to malaria but not malaria. So she needs to get further tests. So they have to force some drug on her, on the girl, and then because so she now asked, so why are you? She's not positive. So why are you recording her to be positive? He said that once anybody come and we test with RDT, was report this thing. So and then in the long run, you find out that all of these noise are entering our data, and then you are finding difficult to really predict the actual situation. The actual situation cannot be predicted because there is something wrong with the data. It's because we are privileged to know that there are many that are going on in terms of data manipulation and all that. So all of this brings noise into our data. So information on notifiable diseases such as measles in England and Wales, foot amounts, or classical swine fever tends to be highly detailed and fairly accurate, even though they are coming from abroad. So in contrast, infectious diseases that are largely asymptomatic, such as meningococcal infection, like the CSM, you are looking at cerebrospinal meningitis. So they are asymptomatic in nature, or disease of wildlife may be subject to greater uncertainty in their reporting. Now, I was looking at the report of CSM yesterday. Dolapo, are you here? Can you hear me? You show me the data. Everything was zero. Are we? 0, 0, 0, 0, 0, 0, 0. Yeah. So those are the challenge. So how do we want to? That zero. What does it mean? Are you sure? I don't know until I see the person that took it. Yes. The zero may also mean missing data. So if you someone maybe someone that got it and said, you didn't find it, let's just put zero. Because when you say zero, it means there is no case. But it may also mean missing data. Right? So until you find the source of the information, who recorded the data, that you'll be able to act. So for any specific infectious disease, the stochastic due to observational noise can most readily be quantified as either incomplete reporting of true cases, or misdiagnosis. Now, just like the girl was misdiagnosed. Now, let me say, he was diagnosed correctly, but what happened? The report was wrong, right? But there are also cases of misdiagnosis where the diagnostic tool does not satisfy either the sensitivity or the specificity of the diagnostic tool. Because now, there are certain diagnostic tools that is giving false positive, false negative. Somebody that is negative is saying that it's positive. Somebody that is positive is saying that it's negative. You understand? So those are the issues with diagnostic tool as well. So, and then that's why you see now some people have to, if you test with RGT, the gold standard actually is the microscopy for malaria. Microscopy will light microscopy will pick. Followed by the PCR. It's that's the molecular one that can see beyond all those other ones that we are doing. So we call this both type 1 and type 2 errors. Now, for the measles data from England and Wales, under-reporting is well documented with an estimated 60% of the actual cases being reported. The remaining, they were not unreported cases, 40%. So in contrast, during the 2001 foot-and-mouth outbreak in the United Kingdom, misdiagnoses were frequent from animals infected with other diseases were incorrectly diagnosed as having foot-and-mouth. Although it is unlikely that animals actually infected with foot-and-mouth would have escaped infection because of the strength of the diagnostic tool, that there were misdiagnoses. Now, the recorded number of infected individuals, while recorded, can be represented as the sum of two binomial distributions, which is y recorded binomial. So PRY2 was binomial of PM n minus Y2. So the L there is the probability that a case is correctly reported. The PM there is the probability that a healthy individual is misdiagnosed. N is the total population size. Now, although such considerations are obviously important when interpreting case report data, they do not interact with or influence the underlying epidemiological dynamics of that disease. So now, the true number of cases always tends to the deterministic response, and observations are purely determined by the two probabilities PR and PM. PR and PM. Now, even in recurrent epidemics, it has been shown that observational error affects the amplitude of data. When there is observational error, the amplitude, you know what the amplitude is? The maximum displacement. So we find out that the amplitude is not rising to the level it's supposed to rise. And then some of us who are trying to fix, because the data is having issue, so the amplitude is either the amplitude is down and then your modeling is up and it's not catching up with the trend. So they are far away from each other. So now, not the periodicity. And that's why we advise that before you do your mathematical modeling in terms of fitting model to data, you decompose your model into time series using time series decomposition method. You see the shape, both the amplitude, you can like your data. Since you are using your data with the model, your data can inform some of the parameters you use in your model. So from some of these time series you are doing, you can estimate the amplitude of your cycle you are seeing from the data and use it in the model, so that when you are capturing your model can capture the size of your amplitude from the data, because you are factoring the value into your model, you capture it exactly. And then, so these are some of the things that reason why we advise that you should decompose your data before you go ahead. So now, observational noise does not impact epidemiological dynamics. It modifies only the reported data. Like the noise has to do with the data. The underlying epidemiological dynamics, like some of these clinical epidemiological parameters, like infectious period, incubation period, the recovery rate, and all of that, they are not influenced by that, because those are clinical epidemiological. They are influenced by the clinical epidemiological data. So process noise, a more intuitive and fundamentally different way to incorporate noise is to introduce it directly into the deterministic equation. You can introduce noise, process noise, into your process model. Mechanistic model is a process model. It's customized, and you can put anything, you can add, you can modify, you can change depending on your question. As such, the dynamics at each point in time are subject to some random variability, and this variability is propagated forward in time by the underlying equation. So we are therefore concerned with the interplay between deterministic and stochastic forces, how they cancel out or amplify each other. So now, as a starting point, let us incorporate noise into only the transmission time, and let's psi be a time series of random units derived from a normal distribution with mean 0 and unit variance. That's variance 1. Then the basic equation, assuming frequency dependent transmission, are transformed into, now this is more or less like your SIR model. The SIR model is Now, normally you are supposed to have En, per capita death rate, which is minus beta xyn. This one was not very different, right? Minus mu x. This one was not very different, right? So, but because we are now introducing a random deviates, so which we say f of x over y, a function of these two, then the random deviates from the normal distribution. So this random deviate is a kind of normal distribution between 0 and univariance. Now, showing us that our stochastic model is dependent on the probability distribution, which is normal distribution. So then this one, before we're having only this, your SIR model, right? This one, we just change it to X, SIR, right? So SIR is still SIR, just changing the notation. So, and then you have this. So, what we are doing is that we are introducing stochasticity into this. So, for a generality, a function f of xy has been included. For generality, a function f of xy has been included to scale the randomness in response to the current variable site. So, I'm going to stop here.